In this video, we are going to learn how to use the fundamental theorem of calculus to solve for a definite integral. All right, first of all, let's talk about the difference between a definite integral and what we have been working on, indefinite integrals. So let's head up here. Here is what an indefinite integral looks like. You have the elongated s and the dx, that's the notation, and you have the integrand, the function. And the answer to an indefinite integral is just the antiderivative plus c. Your answer is an equation. Now, a definite integral looks like this. All right, you add in your left endpoint A and your right endpoint B. That's the big difference. Now you have a definite area from A to B. All right, so your left endpoint right here from A to B, your left endpoint goes on the bottom of the elongated S. That is called the lower limit of integration. And your right endpoint goes at the top of your elongated S. And that is called the upper limit of integration. To solve for a definite integral, there are two steps. The first step is finding the antiderivative equation, just like it was for an indefinite integral. We will call the antiderivative equation g of x. The second step is you just plug your endpoints into that antiderivative. So you take the upper limit of integration minus the lower limit of integration. So g of b minus g of a. Your answer will equal a number, all right, which is an actual area. All right, so that's the biggest difference. All right, an indefinite integral, your answer is an equation plus c. For a definite integral, your answer is an actual number, that is an area. Okay, to help you understand the calculus notation inside of this box, right here, this is the notation for antiderivative. And we are calling that antiderivative g of x. And then over here, this is a definite integral, and the answer to a definite integral is g of b, your upper limit of integration, your right endpoint, minus g of a, your left endpoint, your lower limit of integration. So let's go ahead and try example number 1. Our integrand, the function that we're taking the antiderivative of, is the square root of x. In order to take the antiderivative of that, we only have two options. It's either the power rule or u substitution, unless you just know it. So we have to rewrite it so that we can use the power rule. And if you remember, the square root of x is the same as x to the 1/2. Now we can use the power rule on x to the 1/2. So the first step is we find the antiderivative. Our antiderivative, using the power rule, we add 1 to the exponent. So 1/2 plus, if we just write it here, plus 2 over 2 gives me x to the 3 over 2, and we put the same number on the bottom, plus c. So there's the first step. Now let's simplify this. We always want to simplify so it's easier to plug in. So to divide by a fraction, we simply multiply by the reciprocal of this. So we get 2/3 x to the 3/2 plus c. So there's my first step. Now that we've taken the antiderivative, the notation has dropped out. The big elongated s and the dx have dropped out. So to help us remember the endpoints, there's a notation that we use in calculus at the end of the first step of the fundamental theorem of calculus. We use brackets, and we put our endpoints on the bottom of the bracket, our left endpoint, the lower limit of integration, and at the top of the bracket, our right endpoint, our upper limit of integration. So after the notation drops out, the big elongated s and the dx, we put a bracket after our antiderivative to help us remember there's still another step. Okay, the second step is we plug in. All right, we take our upper limit 4 and we plug it into the antiderivative g. And then we subtract off, we plug in our lower limit, our left endpoint. So it looks like this. As I plug in 4 into my antiderivative, I get 2/3 times 4 to the 3/2 plus c, and then I plug in 1 to my antiderivative. So 2/3 times 1 to the 3/2 plus c. Now, what's going to happen to the plus c's? Right here we have a positive c. If I distribute this negative, this right here becomes a negative c. All right, so the c's are going to cancel out. All right, so in a definite integral, you never have to worry about plus c. Okay, when I plug in 4 into my antiderivative equation, I get 5.33. And when I plug in 1 into my antiderivative equation, I get 0.667. And then when I subtract, I get 4.66. And that is an area, so we can call it units squared. That is the area underneath the curve of the square root of x from 1 to 4. All right, and then what happens to plus c? Once again, plus c's will always cancel out. You never have to worry about plus c in a definite integral. Let's look at example number 2. Our integrand is 10x to the negative 1.5, and our limits of integration are from 4 to 9. So our first step is we find the antiderivative. We call it g of x. This is going to be a power rule. The 10 comes along for the ride. When I add 1 to my exponent, negative 1.5 plus 1 gives me negative 0.5. And I put the same number on the bottom. So there's my power rule. Now, of course, I want to simplify that. So my antiderivative becomes 10 divided by a negative 0.5 gives me negative 20x to the negative 0.5. And then I use brackets to bring along my limits of integration. All right, so there's the first step to the fundamental theorem of calculus. The second step is we plug in. We plug in the upper limit first, so g of 9, and then we plug in our lower limit. All right, it is always top of the bracket minus the bottom of the bracket. All right, when I plug in 9, I get negative 20 times 9 to the negative 0.5. When I plug in 4, I get negative 20 times 4 to the negative 0.5, and I get the values, negative 6.67, and I get 10 right here, so that gives me positive 3.33 units squared. So the area under the curve of 10x to the negative 0.5 from 4 to 9 is 3.33. Okay, my third example. This is a composite function. All right, so we are going to have to use u substitution to find the antiderivative. So let's practice our u substitution. All right, now don't worry about the 30. Let the 30 come along for the ride. We're only going to do u substitution on this part of it. So my inside function, of course, is 2x plus 1. So my first step, u is 2x plus 1. The second step, I write the differential, so u becomes du. I take the derivative. The derivative of 2x plus 1 is 2, and I toss dx on the end. Now I'm going to go up and diagram. The 30 is going to come along for the ride. This piece right here is going to become u squared, and what's left? Dx is left up there, so that's what has to be by itself right here. So my adjustment is going to be to divide by 2. So for my third step, my new and improved differential is 1/2 du is equal to dx. All right, the fourth step, I rewrite the integral. The elongated s comes along for the ride. The 30 comes along for the ride. 2x plus 1 squared is getting replaced with u squared. And what do I replace dx with? Hey, dx is now equal to 1/2 du. So I have rewritten my integral with u's and du's. All right, the fifth step, I'm going to take the antiderivative. So the 30 comes along. The 1/2 comes along for the ride. The notation is going to drop out. The only thing that I'm taking the antiderivative of is u squared. And that, of course, is a power rule. So that becomes u to the third over 3. And then I use brackets to bring along my limits. All right, if we simplify and plug in u, 30 on top divided by 6 on the bottom is going to give me a 5 out front. So 5u to the third from 1 to 2, and now I plug in u, 2x plus 1. So there is my antiderivative equation. And remember, we want to call that g of x. There is our first step of the fundamental theorem of calculus, finding the antiderivative equation. Okay, the second step, now we plug in. We plug in our upper limit, the top of the bracket, minus the lower limit, the bottom of the bracket. All right, when I plug in 2, I'm just using my calculator table. I'm putting my antiderivative in y equals, and I'm going into my table. When I plug in 2, I'm getting 625. When I plug 1 into my antiderivative equation, I am getting 135. And when I subtract, I get an area of 490 units squared. So that is the area under the curve of 30 times 2x plus 1 squared from 1 to 2. That is the fundamental theorem of calculus. Thanks, calculus.